In this problem, we are asked two questions. So we are asked to calculate free energy change for this reaction under the conditions given, and we are asked to actually determine the equilibrium concentration for the same reaction. So we're going to first answer the first question. So we know that free energy change actually depends on two terms. Can be determined by this as a sum of some standard value, which is calculated under conventional standard conditions, and another term that depends on the concentrations of the products and reactants. So we'll have RT, R is our gas constant, T is our temperature in kelvins, logarithm of the ratio, and in the numerator we'll put concentrations for the products of this reaction, and in denominator we will put the concentration of one reactant that we have here. And of course, water is another one, but for water the concentration is 1 molar, right? We assume. So this value is tabulated. And we know that for the hydrolysis of ATP into ADP and inorganic phosphate, we have this value equal to 30.5 kilojoule per mole. Because it's kilo, we need to multiply by 10 to the third. And let me actually move it to another line, otherwise I will not be able to fit. So minus 30.5 by 10 to the third, and now it's in joules per mole, right? Because gas constant is in joules per mole per Kelvin. And in those units, it will be equal to 8.314, and we multiply by the temperature in kelvins. Here we're given the temperature is Celsius, we need to convert. It's going to be 310 kelvins. And we'll multiply by the logarithm of the ratio. And here, the concentrations are given in millimolar units. When we plug the concentrations into the equation, they're supposed to be in molar. And of course, it's okay to leave some of the units as millimolar if those units cancel out each other, right? But here we have another concentration. So let us convert everything into millimolar. So concentration of ADP in molar will be equal to 10 to the minus third. Concentration of inorganic phosphate in molar is going to be equal to 10 to the minus third. And concentration of ATP will be equal to 3 by 10 to the minus third. And so once we calculate the numbers, it's going to be equal to minus, because this value will be so we can cancel out that. It will be less than 0, so the overall term will be negative, and plus we'll have another negative term. So now we are pretty sure that the overall energy will be negative, minus 51. Actually, let me calculate, because I have the answer in millimolar. I mean in kilojoule per mole. So I'm going to recalculate. And logarithm of the answer multiplied by 8.314 multiplied by 310. And so this term itself is going to be equal to minus 20,635 joule per mole, right? And so we are adding 30,500. And as a result, the value will be minus 51,135 joule per mole. Or we can say that it's going to be equal to about minus 51.1 kilojoule per mole. Okay, so now let us address the second question, the equilibrium constant. So the equilibrium constant, by definition, is actually the ratio between equilibrium concentrations of the products over that of the reactants, right? But actually, these are not equilibrium concentrations. We don't know the equilibrium concentrations. What we do know is free energy change under standard conditions. And we know that actually, I'll continue writing here, sorry for that. Actually, our equilibrium constant can be calculated based on the free energy change under standard conditions as E minus delta G naught prime over RT, right? And so we can calculate it as plus, right, because this is our delta G naught prime, it's negative. So when we put minus delta G naught prime, it will be plus 30.5 by 10 to the third over 8.314 over, we can do 310. The temperature will not affect much the equilibrium constant though. So 30,500 divided by 8.1314 divided by 310, and it will be about 11.8. And now we need to do the E function, and so it's going to be around 1.4 by 10 to the 5. Okay, and so what if we are asked to actually determine, based on the equilibrium constant, whether or not the reaction is spontaneous under standard conditions? How do we do that? We know that equilibrium constant should be more than 1 for the standard free energy change to be, negative, right? And so if we are given just the equilibrium constant, or we have calculated the equilibrium constant based on the equilibrium concentrations given, we can determine whether or not this reaction will be spontaneous as written under standard conditions by the value for equilibrium constant. Please don't confuse delta G with K equilibrium. Delta G is supposed to be negative for the reaction to be spontaneous, but equilibrium constant is supposed to be more than 1 for the reaction to be spontaneous under standard conditions.